we are going to start with the first chapter, that is number system. Now children, you are already aware of various types of numbers that you have studied in your previous classes, that is natural numbers, whole numbers, integers and rational numbers. Out of these, let's recall these numbers very quickly. The counting numbers 1, 2, 3, 4 up to infinity, they are known as natural numbers. Whole numbers are the numbers starting from 0 and go on up to infinity. Integers have negative counting numbers, the number 0 and the positive counting numbers, they are known as integers. And rational numbers are the numbers in the form of p by q, where both p and q are integers and q is not equal to 0. They are known as rational numbers. Now children, the question arises, what was the need to extend the number system from natural numbers to rational numbers, and later on we will study up to real numbers. So let us see. Now there are 4 basic operations in mathematics: addition, subtraction, multiplication and division. Now let us check out in the set of natural numbers whether all the 4 basic operations are possible or not. Now if I take addition, 2 plus 3 is equal to 5, yes, it is a natural number. Any kind of addition will always be true in the set of natural numbers. If you talk about subtraction, if I take 5 minus 3, it gives me 2, which is very much a natural number. But if I talk about subtraction of the type 5 minus 5, there is no number to represent this kind of subtraction in the set of natural numbers. So, the mathematicians felt the need to introduce a new number, that is 0, in the set of natural numbers, which gave rise to a new set of numbers which was known as whole numbers. So, the counting numbers along with the number 0 together constitute whole numbers. Now, in the set of whole numbers, addition is possible, subtraction of 3 minus 2 equal to 1 is possible, 3 minus 3 equal to 0 is possible, but what about 2 minus 3? Again, there is no number to represent this kind of subtraction in the set of whole numbers, which gave rise to the new numbers which were negative counting numbers. So, with the introduction of negative counting numbers, a new set was introduced, that was a set of integers. So, integers contain negative counting numbers, the number 0 and the positive counting numbers. Now, in the set of integers, addition was always possible, like 3 plus 2 is equal to 5, minus 3 plus 2 is equal to minus 1, minus 3 minus 2 is equal to minus 5. All these are integers, or minus 3 plus 3 equal to 0 is also an integer. So, with addition there was no problem. Subtraction is again possible in the set of integers. 3 minus 2 is equal to minus 1 is an integer. 3 minus 2 is equal to plus 1 is an integer. 2 minus 3 is equal to minus 1 is also an integer. 3 minus 3 equal to 0 is also an integer. So, subtraction was also possible in the set of integers. Let us see multiplication. 3 into 2 is equal to 6 is an integer. Minus 3 into 2 is equal to minus 6 is also an integer. Minus 3 into minus 2 is equal to plus 6 is also an integer. That means multiplication was also possible in the set of integers. Let us talk about division. 6 divided by 3 is equal to 2 is an integer. 6 divided by 6 is equal to 1 is also an integer. But what if I write 3 divided by 6? That makes it 3 upon 6, which is equal to 1 by 2. There was no number to represent this kind of division in the set of integers, because we have only positive and negative counting numbers along with number 0 in the set of integers. We don't have the numbers of this type. So, in order to make this kind of division possible, mathematicians felt the need to introduce the new types of numbers which were known as rational numbers. They were in the form of p by q, where both p and q are integers and q is not equal to 0. Now, in the set of rational numbers, all 4 basic operations were possible. Now, let us talk about the decimal expansion of these rational numbers. Suppose if I take a number of the type 2 by 5, it is a rational number, its decimal expansion is 0.4. If I say 7 by 5, it gives me 1 by 4. What if I take 7 by 3? It gives me 2.3333 and so on. If you divide 7 with 3, you get 3 2s are 6. Then you put a decimal point, 3 3s are 9, and you will see that you will keep on, and this is a never ending division. It will never stop. So, these two types of decimals which stop after some time, they are known as terminating decimals. Terminate means which stop after some time, and these are known as non-terminating, but they are repeating. So, they are known as non-terminating repeating decimals. So, when we talk about the decimal expansion of rational numbers, so rational numbers after division, either they give us terminating decimals or they give us non-terminating repeating decimals. Now, let us see, without actually dividing, how can we check whether the given rational number has a terminating decimal representation or a non-terminating decimal representation? Now, suppose you have a number in the form of p by q. So, basically what we do is, we first find out, step 1 is that we make sure that p and q do not have any common factor, that is, they are co-prime numbers. If there is anything common, just cancel it out. Step 2, we see the prime factorization of the denominator. In this case, it is q. So, what is the prime factorization of the denominator? If it contains the factors of the type 2 raised to the power something and 5 raised to the power something, then we say the given rational number has a terminating decimal. If the prime factorization of the denominator has any factor other than 2 and 5, suppose you have 3 also in the prime factorization of q, then it will be a non-terminating but repeating decimal expansion. Let us take for example, if I take a number, say 7 upon 32. Now, 7 and 32 do not have any factor in common. So, our step 1 is over, that is both p and q are co-prime. Second step is the prime factorization of the denominator, which is 32 in this case, which is equal to 2 raised to the power 5, or we can say 2 into 2. When you do the, I hope all of you know how to do the prime factorization. So, that gives me 2 raised to the power 5. As the prime factorization of the denominator contains only 2's, then we can say it is a terminating decimal. So, if the prime factorization of the denominator contains only 2's or only 5's or a combination of 2 and 5, we say it is a terminating decimal. Any factor other than 2 and 5 in the denominator will make the decimal expansion non-terminating and repeating. Let us take another example. Suppose I say 7 upon 125. Again, in 7 upon 125, they both are co-prime. There is nothing common in these two factors, these two numbers. So, what is the prime factorization of the denominator in this case? 125 is equal to 5 cube. Again, we can say it is a terminating decimal. If I take a number of the type, say 7 upon 20, it gives me 7 upon 2 square into 5. The prime factorization is 2 square into 5. So, again, as the denominator contains only 2 and 5 in the denominator, we say it is a terminating decimal. What if I take 7 upon 60? The prime factorization of 60 will be 2 square into 3 into 5. So, other than 2 and 5, there is one more factor, that is 3 in the denominator. That means this type of decimal expansion will have a non-terminating but repeating decimal, that you can actually try out by actual division and you will come out with the same results when you divide. Okay. Now, let us go back to natural numbers. Suppose I pick up any natural number, say 4. Can I say that this number is a rational number? Let us check out. I can write 4 as 4 upon 1, where both p and q, it is in the form of p by q, where both p and q are integers and the denominator is not equal to 0. So, can I say it is a rational number? Similarly, if I pick up any other rational number, say 5, natural number, say 5, it is again in the form of p by q, 6, 7, 8, 9, 10, so on. So, can I say all natural numbers are rational numbers? We can say yes. Similarly, I want to check whether whole numbers are also rational numbers. Yes, all the numbers are same as natural numbers except the number 0. So, let us try out for 0. 0 can be written as 0 by 1 or 0 by 2 or 0 by 3. There are so many ways of writing 0. They all are in the form of p by q, where both the numerator and denominator are integers and denominators are not equal to 0. Hence, can we say 0 is also a rational number? Yes. So, now can I make a statement that all whole numbers are rational numbers? Now, let us check out for integers. Take any negative number, say minus 3. That can also be written as minus 3 upon 1, which is in the form of p by q, where both p and q are integers and denominator is not equal to 0. So, I can say all integers are also rational numbers. So, now can we come to the conclusion? The smallest set of numbers in the beginning was the set of natural numbers, which gave rise to the next set of natural numbers was whole numbers, which is the addition of one more new number, that is 0. With the addition of negative counting numbers, it gave rise to a set of integers, and then we had a set of rational numbers with the introduction of the numbers of the type p by q. And that means from now onwards, when we simply say rational numbers, that means they include all type of numbers, whether they are natural numbers, whole numbers, integers, they all are rational numbers. So, instead of calling their names separately, natural numbers, whole numbers, integers, we will simply call them rational numbers. That means rational numbers contains all types of numbers which you have studied till now. Now, let us talk about the numbers other than rational numbers, which do not come under the category of rational numbers. Now, as I just told you that rational numbers have two types of decimal expansions. One is terminating decimal and second is non-terminating repeating decimal. There are one more types of decimals which are known as non-terminating and non-repeating. Right? Terminating means which stop after some time, say 3.5 or 4.75 or 2.195 and so on. They can stop after maybe 1 digit, after 2 digits, after 3 digits, but they will stop after some time. Non-terminating repeating decimal is like say 2.73 bar, means the 2 digits will repeat themselves again and again, or 3.52 bar or 4.9 bar and so on. They can be non-terminating and repeating decimals. But there are decimals which are neither terminating nor repeating. 1.71729583645 and they will just go on and there is no repetition, as you can see. Obviously the digits will repeat themselves but not in a proper manner. So they are known as non-terminating and non-repeating decimals. For example, if you remember in class 8 you must have studied about root 2, square root of the numbers. Now if you actually find out the square root of the number 2, it will come out as 1, its decimal expansion will be 1.4142 and so on, and if you just keep on finding the square root further, you will find the digits will not repeat themselves in a proper order. So this is known as a non-terminating and non-repeating decimal. Now these type of numbers which have a non-terminating and non-repeating decimals, they are known as the set of irrational numbers. They are known as irrational numbers. Now what are irrational numbers? They have a non-terminating and non-repeating decimal expansion. So can we say that all rational numbers are irrational? No. Are all irrational numbers rational? No. They are totally two different set of numbers. One set is a set of rational numbers, another is a set of irrational numbers, and combining these two sets, they are known as real numbers. Now in the set of rational numbers, I will not repeat again and again, they automatically contain natural numbers, whole numbers, integers, fractions, all the type of numbers, right. That means they have a terminating decimal expansion or non-terminating repeating decimal expansion, whereas in irrational numbers we have only non-terminating and non-repeating decimal numbers. So these two sets combining together give rise to a new set of numbers which is known as the set of real numbers. Now let us understand these irrational numbers in a little more detail. Like I told you, root 2 is an irrational number. What do you say about root 3? That is also an irrational number. When it comes to root 4, we can write it as root 2 square. Now square root means the order of this is 2 and here the power is also 2. So actually they get cancel out each other and we get the number 2. If I talk about 5, root 5 is an irrational number, sorry. So this root 4 is actually a rational number. Root 5 is again irrational number. Root 6 is an irrational number. Root 7 is irrational. Root 8 is also irrational. Root 9 can be written as under root 3 square. That means this will also be equal to 3, which is again a rational number. Again root 10 is an irrational number. So moving in the same manner, when I will come to the square root of a perfect square number, say next number is 16, that comes out to be under root 4 square, which gives me 4, which is a rational number. But any other number between root 10 and root 16 will all be irrational numbers. After root 16, when we move on to root 25, that will be under root 5 square, which is equal to 5, which is again a rational number. I hope you understand. Whenever we take the square root of a perfect square, it comes out to be a rational number, and the square root of any other number will be irrational. Now let's look at the cube roots also. If I talk about cube root of 1, that can be written as cube root of 1 cube also, which is equal to 1. Cube root of 2, we cannot take it out of the radical sign, so it is an irrational number. Cube root of 3 is again irrational. Moving on and on, even if I write cube root of 4, this will be cube root of 2 square. Since these two numbers are not matching each other, we cannot take it out of the radical sign and hence it is an irrational number. cube root of 5, 6, 7, 8, and then cube root of suppose 27 I find out. I am skipping out all the numbers in between because none of the number in between, I'm sorry, 1 minute. If I take cube root of 8, that comes out to be cube root of 2 cube, which is equal to 2, because whenever the order of the radical sign and the power of the number are same, they get cancelled out and we get the number itself 2. So cube root of 27 will be cube root of 3 cube, which is equal to 3. So this is a rational number, again a rational number. Okay. Next, cube root will be of 64, because it can be written as 4 cube, which is again equal to 4, which is a rational number. It means the cube root of any perfect cube will always be a rational number, whereas the cube root of any other number will be irrational. Okay.